So in this example, we're going to do a very straightforward application of complex numbers. It's fairly easy to do, and it shows the power of complex numbers, really, what they can be used for with this whole principle of the real and imaginary parts. So we've got two resistances here in the circuit, Z1 and Z2, and obviously, as we've said before, an impedance, Z represents an impedance often, and the real part is the resistance that's in the circuit, and the complex represents whether it's an inductance or capacitance. So what we've got here is two impedances in series, and we're going to add them together. Then we're going to, from this, we're going to use this to find the current. And remember, we find the current using Ohm's law, which is, generally speaking, we're looking for I, sorry. So we'd find I from V divided by R, the resistor. But in this case, it's going to be the impedance, which is this total Z. Let's put ZT. So Z1 plus Z2 will give us a total resistance. That'll be the first thing we'll do. So what we'll do is we'll work out what Z total is by simply adding these two together. And this shows the power of having in rectangle when you're doing adding. It's easiest in rectangle. And then we'll convert that to a polar form of a complex number. So then we can use that as our voltage together with our total impedance, and we can work out what the actual current is in this circuit. Incidentally, this says zero angle because that's our reference point usually. You can have a phase angle of voltage, but it's usual to use that as your reference point, and then reference the rest of the circuit in relation to that. Okay, so let's have a look. So we need to add together Z1, Z2. So Z total equals Z1 plus Z2. And that's easy enough. It's just 3 and 2, so 5, and 4 and minus 5. So I get minus J, just 1J. Okay? So then I need to convert that into polar. And remember, I showed on the previous video how easy that is to do with your calculator. But take my word for it, in this particular case, to save time, we've got the angle in polar will be using these numbers. So the modulus of Z total would be 5 squared, that 5 squared, plus 1 squared, which obviously is 1. So that gives me the square root of 26. Now I could put that in my calculator and get that total result, but that's a whole proper answer. It's not got any rounding errors from converting it to decimal by doing the square root, so I'll just leave it as it is. Now the angle, the theta of this, would be the inverse of tan, minus 1. 1 over 5 will give me 11.31 to 2 decimal places. Okay, and it's a minus sign because if I plot it, it's like thus. It goes, the real part is 5. So 1, 2, 3, 4, 5. And the imaginary part is minus 1. It's going to be like that. Okay, so not much of an angle, so that 11 degrees sounds about right. So 1 in 5 angle. Okay, so minus 11.31. So that's that bit. And now to find the current equals V over Z total, which is this 10 of an angle of 0 divided by this angle, which is 26, square root of 26 is the modulus, and the angle is minus 11.31. So that's going to give me, apparently 10 divided by root of 26 gives me 1.96. Sounds reasonable, because square root of 25 will give me 5, and that will be 2. 10 divided by 5 will be 2. So 1.96 looks reasonable. And the angle's easy enough to find. Subtract a minus, it becomes a plus. So it just becomes 11.31. So that's my result. If I plotted that, it would look like this. Okay, so it'd be the modulus would be, that would be 1.96 long, and that angle would be 11.31 degrees in a positive way, positive direction. You can convert it back to rectangle if you wish. I haven't done it, so I don't think it's necessary. This is really useful. It tells us the magnitude of the new waveform, and it also of the current in this case, and it also tells us its phase angle. So the phase angle of the current in relation to this. So 1.96 amps with a phase angle of 11.31 degrees. Okay, so that was easy. I think you'll agree that was straightforward. Nothing difficult in that. So that's the power of complex numbers. And the results give us a nice feel of what's going on in the circuit. This is hence why electrical engineers like complex numbers.